Hello, and welcome to the YouTube channel Citizen Scientists for Truth. This channel is my idea, it's my invention, it's a way of sharing information among citizen scientists. There was a time when most of the research was being done by laboratories, governments, corporations. Now with technology spreading out in various exciting ways, it's possible for ordinary people to do the same kind of measurements that are being done by national laboratories, by governments. And so it's possible for citizens to take control of these important measurements that are going on, measurements that affect us, measurements like how much radiation is there in my food. And when I say citizen scientist for truth, I don't mean that I have the truth and I'm going to give it to you. It means that I am seeking the truth. And I'm working with you, listening to your comments and criticisms, and trying to figure out what's right together. Well, I should say I'm a physicist, and I've been measuring radiation for most of my career. Not necessarily food, actually, but I measure the radiation in medical products, in our body. I'm the type of person that learns much more from doing things than reading about them. I have downloaded books about radiation in food, but I feel like I'm really learning more by just rolling up my sleeves and doing these measurements myself. And I think you'll find that there are some of you that are the same way. I also think that this makes it easier for me to explain things because these are first-hand things that I'm doing. So let's go. Fukushima has changed the, how should I say it? It's changed the landscape of this world in relation to radiation. Radiation from Fukushima has certainly spread through the Pacific Ocean, particularly among the bluefin tuna that travel great distances. When they come from Japan, they take the radiation with them. The radiation travels through the water, through the air, and even in food that's exported from Japan and Asia, China, Korea. So there are many pathways for this radiation to go out into the world, so it really reaches everywhere. And it's not just Fukushima, there's radiation left over from Chernobyl. There's certainly been, there's probably been nuclear accidents that we haven't even heard about. I think that, at least my personal view, that we can't always trust corporations and laboratories to really be having our best interest when they're doing their measurements. So it's a good thing for us to measure it ourselves. So radiation in food, what people want to know, I'm sure what you want to know, is like which foods are affected, how much radiation is safe, how can I get radiation out of my body, and who can I trust to measure it? So these are the things that we're going to talk about on this channel in these upcoming episodes. What I really have to offer here is a techniques for measuring radiation, where we can measure low levels of radiation in food accurately and understand what it means using a simple device, this Geiger counter. I'm using the Radiation Alert Inspector EXP with an external probe. This seems to be one of the popular Geiger counters out there when you balance cost and functionality. It seems to be a fairly good choice. My friend Anti-Proton, you can find him on YouTube, has done some comparison studies with different types of Geiger counters. I recommend looking at his YouTubes, they're very informative. It would be nice if measuring radiation was as simple as measuring the temperature of food. And actually in some ways it is. I mean, operationally, like when we really just do the measurements, when we hold the Geiger counter up to something, basically it's not that complicated. But being able to do it in the right way and to interpret the results, that's the key. And that's what we're going to focus on in this video series. So with radiation, unlike temperature, which really just has one flavor, just how many degrees is something. Radiation has many flavors. There are many different types of radiation. There's many measurements to be made. And so what I like to think is that this video series is going to ferret out, it's going to come up with a simple test that may not tell us everything that somebody in a national lab can measure, but it can tell us enough to know whether what we're eating is safe. And that's the important thing. So the two general classes of radiation are ionizing radiation and non-ionizing radiation. So ionizing radiation is nuclear waste, fallout from nuclear weapons, dental x-rays, CT scans, that type of thing. Non-ionizing radiation is the kind you're going to find in a microwave oven, a cell phone, a radio tower. It's generally assumed that ionizing radiation is the only one that's dangerous, but in fact, non-ionizing radiation can also be dangerous. This can be a topic of something down the line. But for now, we're going to focus on ionizing radiation. So whenever I say radiation, I mean ionizing radiation. I'm not going to say ionizing radiation every time. Okay, so now when we talk about ionizing radiation, there's three basic types of that: alpha radiation, beta radiation, and gamma radiation. And I don't want to turn this into a big discussion about physics, so I'm not going to go too into detail about what these really are, but just that the alpha radiation is the least penetrating of the three. Beta is sort of middle, and gamma is the most penetrating. Gamma is also very akin to X-rays. So we're going to focus actually on beta radiation in these measurements. It turns out that the beta radiation is better suited for these Geiger counters. I should say the Geiger counters may be better suited for the beta radiation. When you're doing measurements of very low quantities of radiation, the Geiger counters work the best when you do beta, because it turns out that the beta particles have a much greater interaction with the sensitive tube inside this Geiger probe. And so it allows us to measure things in very low doses to make more sensitive measurements. So that's why I'm using beta particles. And within beta particles, we can have low energy and medium energy, high energy. There's a whole spectrum of energies of beta particles. For example, cesium-137 is about, we measure energy in MeV, million electron volts. You don't really need to know what that means, but it's just a unit of energy of these particles. So cesium-137 is about half an MeV. Potassium-40, which is a naturally occurring radioisotope, it's about 1 MeV, and strontium-90, yttrium-90, which actually, strontium-90, which decays very quickly to yttrium-90, gives off a 2.2 MeV beta particle. And we can distinguish between these things using aluminum plates. If we put these aluminum plates between our food sample and the Geiger tube and make multiple measurements, 1 plate, 2 plate, 3 plates, like that, and plot the results, we can tell, we can at least infer an estimate of the energy. And that gives us a good idea of what it is. I mean, if we had to choose between all the possible radioisotopes, it would be very difficult to know what you're looking at. But if you limit the spectrum of radioisotopes that you're looking at to the ones that are, say, fallout from a particular nuclear accident, then you can start making some implications about what you're seeing. Units of radioactivity have been in the news a lot, and it can be very confusing. Sieverts, millisieverts, microsieverts, rads, rems. There's a lot of things out there. And those are terms that generally talk about how much radiation is traveling into my body from something outside. Can be also from the inside too. But that's how much radiation absorbed into my body. I'm going to talk about something that's a little bit simpler. It's just the quantity of the thing that's emitting the radiation. How much plutonium, how much cesium, how much of the stuff is in my food. And that's measured in becquerels. It's a very simple unit. 1 becquerel equals the amount of radioactive material which gives off 1 disintegration per second. Simple. We most often use becquerel in a kind of density, so becquerels per gram, becquerels per kilogram. We want to know the concentration of the radiation in our food. So that's the way we measure the radiation in our food, is using these becquerels per gram or becquerels per kilogram. And of course, the becquerel was named after the famous French physicist and Nobel laureate Henri Becquerel. Okay, let's talk about food measurement. Now, often food decays slowly enough so that if we were to just take something like a banana and hold the Geiger counter up to it or away from it, you're not really going to notice much of a difference. It's very difficult to know, like, is this something that has radiation or not? Unless, of course, it has a lot of radiation, and you'll be able to tell right away. So we need to measure for a long time, and we need to subtract off this background radiation. You can hear this probe is clicking even when there's nothing around it, because the sun, the stars, the earth all give off radiation. And this radiation is not necessarily constant, so we really have to get an idea of how much background radiation there is, and do measurements over hours or even days to get a good estimate of how much radiation is coming off of our food, especially with these foods that have low levels of radiation. Radiation can be very toxic, so even small amounts of it can be dangerous. So we need to do measurements over long periods of time. And I like to say too that the measurements we're doing are not just to know, is this food, should I eat this food or not? But the radiation in the food is telling us what is going on in our environment. The food is sort of like a vehicle of radiation measurement. So even if it's below, even if the amount of radiation in the food is less than it's dangerous for me, and I can eat it, knowing the amount of radiation in it helps me to understand how the radiation is moving in the environment. Maybe we could even discover an unknown nuclear leak by looking at the food like this. So measuring very low levels of radiation in the food is an important thing to do accurately. There's also not just radiation from nuclear waste, man-made radiation, but there's also naturally occurring radiation. Most of the radiation in the food is naturally occurring. And actually the banana is something that has more radiation than the average food, because the banana is high in potassium. And so the particular isotope of potassium, potassium 40, is radioactive. So when we look at food and we want to measure the radiation, we're looking at the natural radiation combined with the unnatural radiation. And so we have to look at these subtle qualities of the radiation to understand whether this food has been contaminated by nuclear waste or weapons fallout or whatever. There is a radiation that's perfectly fine, that's been in the food since way before we ever had nuclear power plants. And our bodies are used to that. Our bodies disintegrate, have particles in them disintegrating many times per second. Another thing to keep in mind is that the strontium-90 is a particularly nasty component of nuclear radiation, because it looks like calcium to our body. Our body takes it into our bones. And so because of, not necessarily just because of the energy that it's emitting or the quantity of particles it emits, but where it goes in our body is very critical. And it determines this thing called biologically equivalent dose. So turns out that strontium-90 is 300 times more dangerous than something like cesium-137 because of where it goes in our body. Also, when we're measuring food, it's important to keep in mind that the radiation is continually being reabsorbed by the food. So when we measure the radiation, we're just measuring the radiation that gets out. We have to know how much of it, what's the percentage of the radiation that gets out. But we can also do ourselves a favor by reducing the amount of radiation that gets absorbed in the food, by dehydrating the food, getting the water out. Certainly the water particles in food, some food is mostly water. So by getting the water out, we're concentrating the radiation and making it easier to measure. So one of my tools of measurement is my dehydrator. But even if you don't have a dehydrator, there's ways you can get around that. You really need to just get the food up to about 110 degrees, let it sit for 20 hours or so. Even putting it outside in the sun can work. So, if I dry, say, a banana, I dry it into slices like this, and then because the slices are kind of irregular, difficult to measure, I grind them up in a coffee grinder actually, and create kind of powder. And then this powder can then be placed into a planchette. The planchette is a nice device for helping us to make uniform, repeatable measurements. But even in this planchette, even though the sample's only a few millimeters thick, there's still self-absorption. And this is where we have to use mathematics to calculate, mathematics and really physics actually, to calculate how much reabsorption there is. There's actually a theory developed by Baker and Katz back in '53. They published it in Nucleonics journal. How to calculate the amount of self-absorption in a sample. And to do that, we just need to know the thickness of the sample and we call the attenuation constant of the radiation coming out. And that's something we measure, like I said, with these plates. But of course, I'm not going to just trust that theory, whether it works. I've done experiments with it. I created a number of samples of something at different thicknesses. Now, and then I calculated the becquerels per kilogram. They should all give me about the same answer. And I found that using this equation correctly allows me to get pretty close results for a wide range of sample thicknesses. So this gives me an idea that the equation is working. We can use it for measuring samples. Now, ideally, you might think, well, just make your samples really thin so that there's no self-absorption. Well, that's true, but what happens is, in some things that do not have a lot of radioactivity, when you make them very thin, the radioactivity is so small that you can't measure it anymore. So what I'm finding is, and this is really hot off the press, is that I'm having to use samples that can have as much as 70% self-absorption, or like say an F of 0.3, only 30% gets out, to get enough radiation into the Geiger counter so that I can make a decent measurement. So this theory of self-absorption is important when we're measuring samples that don't have a lot of radioactivity, these low-level radioactivity like in food. So these planchettes, if you want to get some of them, you can get them. One place to get them is Radiologic, is the GAMA and Associates, and I put the phone number up here. You can call them up and order them for about $1 each. You can get them a lot cheaper if you're willing to buy 1,000 of them. Okay, so once you have the food in the planchette, you still need to hold the Geiger counter close to it but not touching. And this is really important. If you go out and purchase one of these Geiger counters, it's tempting to open it up and start measuring everything in sight. Well, you have to be very careful. If you get some radioactive material onto the tube, it's very hard to get it off. The tube is very thin, it's very delicate. You can't just put it in the washing machine. You have to be very careful with this. So I suggested if you were going out and measuring any kind of radiation contamination outside, the dirt, animals, whatever, put a baggie over the probe so that whatever you're measuring doesn't contaminate the probe itself. It's very important. It's very simple. You just put a baggie over it and close it down as much as you can. The baggie will not absorb very much radiation. You'll still even be able to see alpha radiation too. So you just want to have a very thin, fairly thin baggie, but not too so thin that it'll break. So the slide shows a planchette stand that has ability to put shields. So what this is here is it's a lead, half an inch of lead. It's a shield. It actually comes as a washer with a hole in it, which I plug with a tungsten plug. So it's actually fully solid. But you can integrate these lead shields into the actual stand itself. The stand that I'm showing right now is a simple one that does not have a shield in it. So a lot easier to work with here in the laboratory. This is my kitchen laboratory. So this slide shows a kind of close-up view of this planchette holder. I made it out of PVC pipes and fittings. You could probably make one of these for a few dollars. If you would like information, you can send me an email. I'll put up my email address. I'm perfectly happy to share this with you, how to build this. Someday I'd like to be able to have a nice production version of this that I could ship out to everybody too. But for now we're building them out of PVC pipes. Okay, so let's measure something. That's what we came here for. So potassium chloride is what I'd recommend if you're going to measure something first. Potassium chloride is a fairly good, fairly strong radiation source. So you can buy it at the store under the name of no salt. There's probably other companies that make the salt substitute. The no salt is basically pure potassium chloride granules. Now, if you take the Geiger counter and you hold it up to the no salt, you can hear that the counts are coming much faster. So the no salt has actually got enough radiation in it that you can measure it real time like this. But if we want to measure it quantitatively, if we want to know how many becquerels per gram, we have to do a little bit more carefully than that. This little planchette, I've put 4.1 grams of potassium chloride on it. And so from basic chemistry, we can calculate that translates to 2.15 grams of potassium and 1.95 grams of chlorine. Something we'll go into in future episodes of this show is when you're measuring powders like this, if you look in the manuals of fancy instruments that do these kind of measurements, they like to, not just to have granules, because the granules have gaps and all kinds of things, and it's hard to predict how the beta particles are going to bounce through these holes. They like to solidify it using types of glue. Anyway, we'll talk about this more. I've kind of solidified this potassium chloride by putting a few drops of kind of super saturated water with potassium chloride in it, not to make it into a single crystal, but just to kind of glue it together and then dry it. So this is not going to just come flying out of there. It's not just a powder. If you try putting potassium chloride saturated solution in there and drying it, you'll get all kinds of odd shapes of crystals growing out of it. It doesn't really work very well. Okay. So this particular sample of potassium chloride, because it has 2.15 grams of potassium in it, is going to have 66.7 becquerels. In general, there's 16.25 becquerels in every gram of potassium chloride. So we know this from theory. These are things you could look up on Wikipedia. So when we measure this potassium chloride, this is a very nice measurement because we know what the answer is supposed to be. We can actually use the measurement to calibrate our detector. We'll see how we do that. Now, it's important to understand how much of this potassium is underneath the detector. Now, you might think that, of course, well, all of it is, but the reality is the detector is 1 3/4 inch. It's a little bit smaller than the planchette, which is closer to 2 inches. So what we do is we take the ratio of the area of the Geiger-Müller tube to the area of the planchette, and we divide them. We get that ratio. It's basically 0.7 or 70%. So we figured that when we put all this thing in this planchette, we put the Geiger-Müller tube over the potassium chloride. The Geiger-Müller tube is sitting on top of about 70% of this planchette of potassium chloride. Now, you could argue, well, of course, stuff outside that 1 3/4 inch can decay and come in, and also stuff that's on the inside of that planchette can decay and go out. So if we assume that those are roughly equal, then we can just use that as a first estimate about how much are we really measuring. So I will consider the sample that I'm measuring to be 70% of what's in that planchette when I put it into this planchette holder, as I'll do right here. It's difficult to get it in, dropping it in by hand, so I help out with this little pipe holder. Once it's in, then you can take the Geiger-Müller tube and put it on top of it like this. You can actually use this to support the handle so it doesn't fall over. You can certainly hear the measurements going much faster. With the potassium chloride, it's got enough radioactivity in it so that even in, say, 30 minutes or an hour, you get a very good statistic if you integrate the sample. When I do measurements, I'm always using this total timer feature in the Inspector EXP. And when I do the measurements, I am using this timer function on the top here. Timer function on the top. When you use the timer, you first put it in the set mode, and it displays the time on the screen. You can set it for a certain amount of hours. 0300 is 3 hours. I can set it for as much as 40 hours. Set it down to a minute if you want. But for this potassium chloride, I suggest usually about 30 minutes. You get enough counts so your statistics are good. So you take your measured counts, divide by the time, you get counts per second. We also do measurements of background. So we do the same measurement in the planchette holder with the planchette with everything the same except just no potassium chloride. And we subtract. That way we can get how many disintegrations are we actually getting from the potassium chloride, not just from cosmic rays from the Earth. So we subtract off the background. I do multiply this by 2 because if I had another detector on the opposite side, it would probably measure the same amount. So we divide by the detector efficiency because the Geiger-Müller tube doesn't get all the gamma rays or beta particles or whatever that go through it. So it only detects about, say for betas, somewhere between about 30 and 40%. So I chose to use 38% here. The self-absorption factor, FA, I'm using 44.6%. That's basically calculated from measurements I did of the absorption constant and the thickness. We'll go into that in the future episodes. I have 4.1 grams of potassium chloride in the planchette, and then this 0.7, which is the area ratio of the Geiger tube to the planchette. So when I multiply that 0.7 times 4.1, I get the mass I'm actually measuring. So this comes out to be 19.85 becquerels per gram. But now we know that the potassium chloride is 16.2 becquerels per gram, so we're off a little bit. But that's okay, because we know what the answer is. So what we can do is we can say that our efficiency for the detector in this particular arrangement, you know, for a distributed source in a planchette, this particular energy, it's going to give us a slightly different result. So we can kind of use this to calibrate our Geiger tube for measuring stuff that's kind of similar to potassium chloride, which is actually quite a lot of foods are similar to potassium chloride. So I think it's pretty safe to use, instead of using the 38% efficiency, to use the 46.5. That would give us perfect agreement. So the next thing we're going to do is go off and measure something, a different type of food, and see what we get with that, using this new calibration factor that we just did. Actually, the next thing we'll do is a kind of kelp powder that I found that has a lot of potassium in it, so it's got a pretty good signal. So I appreciate you watching this channel. I look forward to hearing your comments, your feedback, and together, as a team, we are citizen scientists for truth. Come back next time. Thanks a lot.